Everyone can see it fine? Does it need to be zoomed in at all, or is it fine? It's okay?
It's fine.
Okay, cool. Well, good afternoon, everyone. I'm Eric, and so I'll be teaching class today. As far as I know, Dr. Musalek is still out of town, so she hasn't told me anything. So I'll just be teaching today's class. As you can tell, it's all about it's going to be the introduction to complex analysis. And she gave me about 15 pages of notes to cover. And so what I did basically is I compressed it in a lot of places that I think will be easy for us to understand, and I kind of expanded on some other places that I think that she just kind of assumed. But I'll try to show my steps as much as I can. So today, let me just do an outline of what we're going to be doing on at least chapter 21. So today's outline. The first part, we'll be doing the complex numbers and the complex plane. The second part, and if I go too fast on any of this, just let me know. I'll slow down, but I just want to write what we're going to do today, and then I'll pause. The second part is elementary functions. The third part is the polar form. And the fourth part is differential calculus and but we won't be covering that today. Not today. Not in these lecture notes anyways. So let's just dive right in to section 21.2. Section 21.1 is just a page long, and it's no math really, it's just history. So we're going to define our complex number as z, and it's going to be z equals x plus I y, where I, as you guessed it, is the square root of -1. And also in the notes, if we want to extract the real part of the complex number, we write RE and then in parentheses x plus IY. And that's defined as x. And the imaginary part of z is y. Another thing to note. This is just all notation. Z equals x plus IY. That's the same thing as writing z x comma y. And we'll see that used in just a second. Another thing to know is that if we want to know the complex conjugate of z, we're just going to put a minus sign here instead of x plus IY, x minus IY. So z bar, that's how it's denoted as a complex conjugate. Z bar equals x minus IY. Okay, so let's go ahead and just kind of plot what's going on here. So we're going to have our real axis and our imaginary axis. And in her notes and in the book, they just denote it as this x and y. but it's the real and imaginary. So let's plot a point here, and so it has coordinates x and coordinates y. And in her notes, she says to think of complex numbers like vectors, basically. So whenever we want to find the magnitude of basically like a vector starting from the origin to the point, what we're going to do is basically the same way, and it's called the modulus. So mod of z, that's how it's denoted. Mod of z equals, and it looks very similar to the absolute value symbol. I mean, it's basically the same thing, but for complex numbers. So that equals x squared plus y squared, and that's going to give us this length, as you probably could have guessed. I know this isn't really anything new so far. One more thing is that if we want to find the distance between two different z values, so let me just plot this again. Sorry, if it's so if we have say for example 2 different z values, and we want to find this length, what we're going to do, so she writes this as x2, this is x1. So what we're going to do is probably pretty straightforward, that this length, the value of it, is just the square root of x1 minus x2 squared plus y1 minus y2 squared. Okay, cool. Everyone got that so far? It's okay. I know you probably already know this, but it's in the notes, and I wanted to cover pretty much everything. So next, what I'm gonna do now, I can either write out. I have like a page of what just seems like definitions here. Like, do you want me to just to show y'all, or would you rather me write it out? Because I mean, the example problems after that don't really use the definitions. I'm not going to say they're not important, but do you want to just see them and maybe hold them in your mind instead of, I mean, the notes will be online if you want to.
You can just show them.
Is that okay? That's okay? Okay, cool. So, okay. I'll show hers because hers are typed. But starting right here, and she says that a neighborhood of a point z0 in the z-plane, and by the way, the z-plane is the imaginary plane that we were just sketching, is the set of points z closer to z0 than the radius r. That is, a neighborhood consists of the set of points z such that, and this is the mathematical formula for it basically. And what you'll notice is that it's basically the equation for a circle. And so if this is our circle, this is our radius, it's basically the points inside of the circle. And the notation for it is n of z0, r. So that's the neighborhood. Okay, so The next one is a set. A set of points is connected. She doesn't define what a set is, but she says a set is denoted like that. A set of points is connected if each pair of points can be joined by an unbroken line consisting of a finite number of straight segments, each contained within the set. Okay, so, and I'm just gonna, again, I'll just read through these. We don't really use this in the examples, so just bear that in mind. Just bear with me. But the next one, a point P is a boundary point of S if every neighborhood of P contains points in S and outside of S. A point is an interior point of S if it lies entirely within S. A connected set S is a region. S is an open region or domain if it contains none of its boundary points. And S is a closed region or domain if it contains all boundary points, including interior and boundary points. So, and again, this is, at the bottom here, this is pretty much what I was saying, that a circle of radius r centered at z0 is denoted as this. And so r z0 is, that's basically x0 plus I y0. So that's where the center of the circle is located, and r is just the radius of the circle. So that's probably the only formula that you really need. Okay, is that straightforward? I know there's a lot on that page, but it's definitions that, again, it doesn't seem like we're going to be using. But okay, so just half a page more definitions, and then we'll get into actually solving some stuff. So again, the circle C of radius r and centered at the origin z0 is the units, is the unit circle. She talks about the disk basically and regions, and for those you're just going to use these inequalities here and here. So, for example, the closed circle is this; it's less than or equal to. So it's filled in and has the center at z0. And for an annular region, it's going to look like this. And notice that it's dashed now because it's less than signs. It's not less than or equal to. Or sorry, this is greater than. So anyways, I mean that's pretty straightforward. I think that y'all could have probably guessed that, right? I mean this is nothing too complex. Complicated. It is complex. Okay, so let's just jump right into an example that will probably help illustrate. So, okay, cool. Example 1. Okay, we are asked to sketch the modulus of z minus 1 less than equal to 5. So again, this is our radius, 5. Less than or equal to, that means that all the points in the region are contained within the circle. And this z naught equals -1 plus 0, 5. Sorry, that's awesome. so I mean it's pretty straightforward. We know we know the center of the circle, which is located on the just on the real axis at 1. So put that there, 1. And then our radius is 5. So we'll just roughly circle. So this is at 1, 6, negative 4. I'm sorry, I know. I know. Okay, so, and just one thing to note that it's filled in simply because this is less than or equal to. If it would have been less than it would have had a dashed line. But that, I mean, this is pretty straightforward. She has another example, so we'll just run through that real quick, if everyone's okay with this so far. So we're asked to plot z minus 3 plus I less than or equal to 4. Okay, so again, we just do the same thing. We notice that this is our z naught term, and it's going to be centered at positive 3 and negative 1I. Yes. So positive 3 on the real axis. They call it x and y. So positive 3, and then negative 1 on the imaginary axis. So that brings us here with a radius of 4, because this is our radius. So whatever it looks like at that point. Is that okay? Everyone's good? Okay. Just one more simple exercise, and then okay. I guess let me just show y'all instead of writing this one out. It's pretty simple. I really don't even think that y'all might not even need to write it down. So again, just like the last two, we're asked to sketch what the modulus of z less than 1 looks like. And so, like I was saying earlier, this is going to be the unit circle. These are all going to be the unit circle. They're just going to have slight differences, as you can tell. So, again, the unit with r equals 1, and it's dashed because it's less than, no, I should have had 1 here, 1. Again, it's the same thing, just less than or equal to, so it's filled in. And then this is greater than 1, so it's everything outside of here. That's clear, right? That's okay? Okay. And then just a few more definitions. Again, she doesn't even use these definitions for the rest of the chapter, but they're in there. So the open upper half plane is the set of all points z equals x plus iy such that y is greater than 0. So it's everything basically above the x-axis. The lower half plane is y is less than 0. Right half plane, x is greater than 0. Left half plane, x is less than 0. Straightforward. Very straightforward. Okay, so now I'm going to introduce complex functions. So before we had complex functions. Before we had the complex variable z equals x plus I, y, but here we're going to have something called the complex function, which you basically feed in z to this function, and it's going to give you something out of it. And that'll be clear in a second. So let me just define what a complex function is. A complex function is a function in which the independent and dependent variables are both complex numbers. For which the domain and range are subsets of the complex plane. So a complex function, we're going to call it z of z. So like I said, we're going to be feeding in z into the complex function, and it's going to be equal to u x of y, x comma y, plus I v x comma y. Okay, so that's what our complex function is going to be. Again, the complex variable is like z equals x plus iy. Complex function is our w. So basically what we're going to be doing, we're going to be mapping the complex variable from the z-plane onto a new plane called the w-plane. So let me just sketch that. It might help y'all to like write this to kind of like visualize what we're going to do. But we're going to do an example after this that will clear things up. So this is our z-plane, where we have some domain. Okay, so this is the plane we've been sketching on this whole time. You know, this is nothing new right here. So we're going to take some point z, and what we're going to do is we're going to use, we're going to feed it into this w, and what it's going to do is it's going to put it on a new plane called the w plane. So here, and it's going to give us a range. So this is going to be w of z, and the axis is going to be u and v. Okay. So again, we're just going to be taking our z, we're going to feed it into some function w, and we're going to get out some new values. So now I'll do an example just to make it very clear. So example 3. Okay. So we're asked to determine the range R for W of z equals to 3 plus I z. The domain So the domain basically the domain is the first quadrant in the z-plane. We need to find what the range is. So all we do basically, we're going to write, so let me just write z equals x plus iy. We know this. Okay, z equals x plus iy. We're going to feed that into our w, so w of z equals 3 plus I times x plus iy. Which equals 3 plus ix minus y. And that equals 3 minus y plus ix. And so, if you'll notice, this u x of y, that's what our 3 minus y term is. This v, that's what the x is. Okay, so we're told to plot the range. So let me just plot the domain first. The domain is all values here. So basically plugging in values for x and y, because we're given the values for x and y, it's 0 to infinity, and plugging those in, we'll find that the range looks something like this. At 3, it's going to include all that. Oh, sorry, not below the x-axis. Just, I mean, you find the range just by plugging in values for y and x because we're given this. So, any questions so far? Is it okay? About 30 minutes in. Okay. So, are you still writing, or you're still, okay, I don't know. So that was pretty simple. The next step, so for, like I said today, that's kind of it for part 1. Now we're going to move on to elementary functions. Okay, so the first thing that we're going to do is we're going to derive Euler's formula. And I'm pretty sure everyone's seen this before, but let me just ask you all a question 1 sec. Okay, so this is part 2. Now I have a question for y'all. We're gonna be deriving e to the iy equals cosine of y plus I sine of y. I think we've all seen that before. So I have a question for y'all. In her notes, she just asserts certain steps. Like we're gonna be using the Taylor series to derive this. She just asserts what like the Taylor series for e to the z is, and the Taylor series for what cosine and sine are. Do y'all want me to? I have all the steps right here. I can show you exactly how I derived to that point, or do you want me to just write down what she has? Because I know, maybe some of us haven't seen Taylor series in a while, and it's perfectly okay. But if you want to save time, like I can just show y'all what I have. I don't have to write it down, and I can just walk y'all through it and give y'all the result. What do you think?
You can show us.
Just show us? Okay. So the whole background behind the Taylor series is that we're going to assume some function, any function, e to the x, sine of x, whatever we want, is basically an infinite summation of polynomials. So this is what it looks like. And in deriving the Taylor series, how we do it is we're going to assume it's centered at some value a, and what we do is we plug in a into this equation. So plugging in a gives us f of a, and we'll notice that these will go to 0 whenever we plug in a. So that's how we're going to find the values of our constant c naught. And so how do we find our second value? We take the derivative of f of x. So taking the derivative and doing the exact same thing, we plug in a again, and so we can then solve for our next constant, c1. Doing the same thing for the third constant, same thing for the fourth constant. That's how you find your constants for the Taylor series, and there you go. So this is basically, in the end, what it looks like to just the generic form for a Taylor series. So our first step in deriving Euler's formula is to do a Taylor series for e to the z. So what we do is we have our function, we take the derivative of our function, e to the z, we take our second derivative, e to the z again, and then what we do is we plug in a value of a equals 0. So doing that gives us 1 for each term. And so plugging that back into our Taylor series equation, we end up with this. So rewriting e to the z is going to give us this. Okay? And so our next step, what she does is, so we can, now I know that this is e to the z, but this could have been e to the x, e to the whatever variable we wanted it to be. So let's just go ahead and substitute iy instead of z. And substituting iy instead of z is going to give us this. So that gives us this expression here. And evaluating it, so evaluating all the I squares, I cubes, and all of that, we're going to get a Taylor series with an alternating sign. And we're going to split up the terms. So all the terms with an I still attached to it is going to go here, and all the terms without an I are going to go here. So in the end, we have the same thing, just slightly rewritten. And you'll see why that's important in just a second. Because when we do, so the next step is to, so we did the Taylor series for e to the z. Now let's do the Taylor series for sine. So again, you just pick your function, take your derivative, second derivative, third derivative, evaluate your function at each value of a, and when you plug those in, you'll get sine of x equals this. And this thing looks exactly like what we split the e term into. So you just flip back real quick. So it's going to look like this term right here. So that's why we're doing this. And then I could do the Taylor series for cosine, but why would I do that when I can just take the derivative of the sine term and use that expression? So that's exactly what I did, cosine, and I'm going to plug this into here. And so we did it. We derived the Euler function. Is that clear? Any steps to know? Okay. And all she does is she says that z equals x plus iy. Therefore, e to the z equals e to the x plus iy, which can be rewritten as e to the x, e to the iy. Therefore, e to the z, which is what we have right here. So turn right there. E to the z equals this, what we just wrote down, and substituting in our Euler formula into that, we'll get this expression. So it's just taking it a step further, but not too complicated. So, is everyone Does everyone just have up to above this line so far? Well, this line? So it's okay? Okay. So let me just do a couple things that she wanted to note in her notes. So, what is the modulus of e to the I y? So, we want to figure it out. So, let's just use Euler's formula. So, Euler's formula right here. So, modulus of e to the I y, we can rewrite that as cosine of y plus I sine of y. So that's okay. And then we just take the square root, cosine squared of y plus sine squared of y. That equals 1. What is the modulus of e to the z? What is that? So let's just do the same thing. We had e to the z equals e to the x times cosine of y plus I sine of y. So doing the exact same thing, we would get, sorry, the modulus. It's the square root of e to the x cos. Okay. And simplifying it, you just get e to the x. One last thing in her notes here, she has f of z equals e to the z, and we want to know what df dx is. So what she does is d or dx of e to the z is d over dx of e to the x cosine y. And again, we know the derivative of e to the x is just e to the x. So in the end, we end up getting that it's just e to the x cos y plus I sine y. Sorry. So So the next part is going to be the third part in what we're doing today, which is the polar form. So that's going to be our third, what we're going to start now. So, polar form. Okay. So it's just like, just like you would expect. We're going to have x, y, or real and imaginary, and we're going to plot some point z. Okay. And it's coordinates, and we want to, and an angle is also associated with it, so there's our theta angle. And we want to express it in polar form. So we know that in polar form, x equals r cos theta, and y equals r sine theta. So rewriting z as x plus iy, so that equals r cos theta plus I r sine theta. Factoring out the r, we get that it equals r times cos theta plus I sine theta. And this equals e to the I theta. Therefore, z can be rewritten as r times e to the I theta in polar coordinates. So, and when we want to find the what's called the phase or the argument of z, that's what this theta value is here. So arg of z plus theta, which just equals the arctangent of y over x. Very straightforward. An important note, what we're going to be doing here in a second, we're about to work an example, so you'll see this, but our theta value equals ARG, capital ARG of z plus 2 pi n, or as you'll see written, theta naught plus 2 pi n, where n equals 0, plus or minus 1, plus or minus 2, and this theta naught is our principal argument of z, and it has to be in between negative pi and positive pi. So so let me just start an example so y'all can see this in action. So simple 4. Okay, so we're given z equals 1 plus I, and we're asked to find the modulus of z, and we're also asked to find the argument of z. Okay? So let me just plot it. So 1 and 1. Real and imaginary. Okay. So we want to know what this angle theta is, and we want to know what the length of basically that vector is. So let's find the modulus of z first. So mod of z just equals the square root of x squared plus y squared, and that equals 1 squared plus 1 squared square root of 2. Very straightforward. So the second part, we're going to find the argument of z. Argument of z equals the theta, which equals arctangent of 1 over 1, which equals pi over 4 or 45 degrees. So this was really simple, but it can get tricky, and I'm going to show you how it can get a little bit tricky. So what if it wasn't coordinates 1, 1, but it was coordinates negative 1, negative 1? So instead, this was our point at negative 1, negative 1. And so our theta value would be here, right? That would be our theta value. But what happens if we plug in negative 1 into the arctangent formula? So we would get arctangent negative 1 over negative 1 which equals the arctangent 1/1, which equals 45. And that's not what this angle is. So the idea behind what I was just calling the principal angle, where did I write it? The principal angle here. So we're going to need to rewrite our, we want to find this. And so we know that if we have the coordinates -1, -1, that our theta, the actual value, is 5 pi over 4. Okay, that's what this angle actually is. And if we want to find the principal angle, if we're asked to find the principal argument, let's just plug it into this equation here and solve for theta naught. So doing that, we get equals theta naught plus 2 n pi. So so you can solve for theta naught here. So theta naught equals 5 pi over 4 minus 2 n pi. Now so this should give us values for what the principal angle is, and of course it's 2 pi n because every 2 pi it just repeats itself. So at n equals 0, well, we just get 5 pi over 4, and we're told that the principal argument can't be, or it has to be in between negative pi and pi. So let's try n equals 1. So trying n equals 1 and plugging that in, we get that theta naught equals negative 135 degrees. Cool. So I only have about just 3 more pages and then we'll be done. I'll try to be quick, but okay. So is this okay? Everyone understands? Okay. All right. So let me just, okay, the next thing we're going to do is called the integral power function. So integral power function.
If you go back to the
Yeah.
next page, so then now we have our data going from so we're going counterclockwise, now we're going clockwise? From
Well, yes. So when you measure this theta angle, you always start from the positive real axis and measure counterclockwise. So if we get a negative angle, then that just means that yes, we're going clockwise. But theta is defined as starting from the positive real going counterclockwise. That makes sense. Okay. So okay, the next part is the integral power function, and that is f of z equals z to the n. Okay, so again, just writing down what z is. Z equals x plus iy. You know that. And writing it in the polar coordinates as we did earlier equals r cos theta plus ir sine theta, which equals re to I theta. I'm just rewriting what we previously derived at the very beginning of the flow form. So what happens if we raise each side to the power n? So if we raise z to the power n, we get re to the I theta, all raised to the power n. And we know that, I mean, you just rewriting this is you get r to the n, e to the I, n theta. And that's basically it for this one. So z to the n equals rn cos n theta plus I sine n theta. And this is known as a That's straightforward. That should be pretty straightforward. Now the next one is the complex logarithmic function. Okay. Complex logarithmic function. So what we're going to do is we're going to take the same z function that we wrote just right there, z equals r e I theta, and we're going to take the natural log of both sides. So natural log of z equals natural log of r e to the I theta. Okay. The next step, we're just going to use a bit of algebra. We're going to use the product rule for exponents, not calculus. So using the product rule, we're going to get that this is equivalent to ln of r plus ln of e to the I theta. Okay, and then next we're going to use the power rule. In doing so, we get that that equals ln of r plus I theta ln of e. And as you guessed it, ln of e is just 1. So get ln of r plus I theta. So let's just recall real quick that when we found the modulus of z, so the modulus of z equals r cos theta squared plus r sine theta squared. This equals r. So let's plug this r right there. So therefore, in the end, the formula that we get is ln of z equals the natural log of the modulus of z plus I times theta p plus 2 n pi. So I'm just rewriting this theta as the principal theta plus just because it repeats itself. So again, we're n equals 1, 2, 3. So that's our final equation here. Is it clear? It's fine? Okay. Any questions on that? No? Okay, I'm going to do one example with it. I have one more example left, and then I have a differential equation to solve, and then that's it. We're done with the lecture. So let me just use this equation to show we didn't derive it just for nothing, and then we will solve the differential equation, and then we'll be done. So yeah, okay, cool. So example 5. So we want to determine all possible values of w equals ln of z, where z equals 1 plus I raised to the 1 minus I raised to the 1 plus I. Okay, so that's our problem, and we'll first start by just simplifying this z term. We'll just simplify that z term. So simplifying it, we get that z equals 1 plus I raised to 1 minus I times 1 plus I. Okay? So that's our first step in simplification. Now let's multiply this exponential term together. So we get 1 minus I, 1 plus I. So in doing so, we get negative I minus square root of negative 1 square root plus 1 plus I, which equals 2. So rewriting z, so just substituting that 2 in here, we get 1 plus I squared. And so 1 plus I times 1 plus I equals I squared plus 1 plus I equals 2I. Okay, so we did all that. We basically saw that z equals 0 plus 2I. And let's just draw that on the real imaginary plane. So real imaginary it has 0 real component and then 2 imaginary. So it's going to be 1, 2 right here. This is our what we're looking for. This is our z. Our angle measured from the positive real axis is our theta, which equals pi over 2. So I just took the z that we simplified from the beginning, took it, and then plotted it, and found the argument of z. So now all we have left is to plug our information back into the formula that we just derived on the last page. So this is the formula that we're going to plug it into. That's why we derived it. So again, I'll rewrite the formula here. ln of z equals ln modulus of z plus I plus 2 n pi. So and the modulus of z equals 2. So we get ln of 2 plus I times pi over 2 plus 2 n pi. And what she does is she simplifies it further and just writes ln of 2 plus I pi over 2, 1 plus 4 n. That's our answer. So we were asked to find what the ln of z is, and that's what we did, given this specific value of z. I think that was probably pretty straightforward. This is just algebra simplification, plotting it, finding the argument, and then plugging it into the formula. It's not too bad, right? It's fine. Okay. All right. This is the last example, and then we're done. So the last things. Oh, you're still. You good? Okay. The last thing. Another example. I know why she did this example. I'll explain it at the end, but I know you'll probably be wondering why are we solving a differential equation. But let me just work through the problem, and then I'll kind of explain why. So we're asked to just solve y double prime minus 2y prime minus 3y equals 2e to the 4x. So we need to solve for y. And the first thing to note is that when you have a differential equation like this that's non-homogeneous, so this is not 0 on this side, but it's some function, some value, we're going to have that our y solution is the summation of our complementary solution. So that's what this one is. Complementary solution plus our particular solution. That's our particular solution. So, and I know you all have probably seen this before, but what we do is we first solve the homogeneous differential equation. So for a complementary solution, let's start with that. Complementary solution. So here we go. We have y double prime minus 2y prime minus 3y equals 0. So I'm just rewriting the left-hand side and setting it equal to 0. So we do what we've been doing, all semester when we try to solve these. We're going to assume a solution of the form some constant times e to the mx. And you just take the derivative of that, c1 e to mx, y double prime. Substitute these values back into here. We get c1 m squared e to mx minus 2c1 m e to the mx minus 3c1 e to the mx 0. Factoring out the c1 and the e to the mx, you get m squared minus 2m minus 3 equals 0. And this is our auxiliary equation that we need to solve. So it's just, I mean, again, this is just what we've been doing all semester. Quadratic formula. Finding the roots of this, you get that they are 3 and negative 1. So plugging these roots back into our assumed solution, we get that, equals c1 e to the 3x plus c2 e to the negative x. So that's our complementary solution. For our particular solution, we're going to use the method of undetermined coefficients. Okay, we're going to use the method of undetermined coefficients. So basically what you do for that is you just kind of guess what the function is going to look like for this side. So in our case, we have 2e to the 4x. So let's just guess that our particular solution has the form ae to the 4x, because it is very similar to this, and all we need to do is solve for the value a. So you just kind of guess and check. So for here, we're just going to do the exact same thing we did when finding the complementary. Let's take the derivatives. So yp prime equals 4a e to 4x. Yp double prime equals 16a e to the 4x. And then we just plug this back into our equation here and evaluate it. So I'm just going to write that y double prime minus 2y prime minus 3y equals 2e to the 4x. So what we're going to do is we're going to evaluate it at y equals y. So therefore we get that, plugging in each one of these derivatives and y functions, we get that 16 a e to the 4x minus 8 a e to the 4x minus 3a e to the 4x equals 2 e to the 4x. Simplifying it further, we get 5a e to the 4x equals 2 e to the 4x. Therefore, a equals 2 over 5. So, therefore that makes our solution, the whole solution, y equals c1 e to the 3x plus c2 e to the negative x plus 2/5 e to the 4x. And that is our answer. Everyone got it? Okay, so just one last thing. She said that the reason that we were doing this is because using the method of undetermined coefficients, we got a particular solution of this form, which is simpler than the two-term form of sines and cosines. So I think that's kind of why we're now like introducing this, because we're going to be using differential equations or complex variables to solve differential equations. So I think that's why she just wanted me to introduce this to y'all. But other than that, I think that's it for today. I mean, are there any questions on anything that I covered? I think that's pretty much it. I'm assuming that she's going to post these notes online. I don't see why she wouldn't, but if y'all want, or if anyone wants, I could scan these and then send them to her, you know, as a PDF, and y'all could look what I have, just because I have, like I said, you know, the Taylor series derivation, you know, that I wrote down, that's not in here. So I just let me know, or anyone online, just let me know. But if there are no questions, we're all good. Thank you. I knew 10 minutes early.
She didn't say it was going to be any homework or anything?
Not to me. I mean, I haven't checked my email in an hour. Yeah, in a few hours. So I don't know if she's anything for she's on this.
You know the log out? Huh? You know the log out?
Yeah. That won't turn the projector. Oh, I forgot to power it off. That's what it is.